When I look at the internet, searching for specifications of very low noise 10 MHz oscillators, this is one of the articles I find. Ultra low phase noise 10 MHz crystal oscillators by Jeremy Everard and co-authors. What they find is minus 122 to minus 123 dBc per hertz at 1 Hz offset and minus 148 at 10 Hz offset. And what I have now with my 20 crystal oscillator is minus 126 at 1 Hz and minus 156 at 10 Hz. So it is significantly better by 3 dB at 1 Hz and by 8 decibels at 10 Hz. They also quote what others have written, and it seems minus 122 dBc per Hertz is about the best that one can find on oscillators. They give some references, and it seems that minus 122 dBc per Hertz at 10 MHz is about the best that is available for crystal oscillators. In this article, 6 oscillators are being used to combine in order to get a lower noise floor. They report minus 182 for the flat noise floor at 10 MHz. That is 6 decibels higher noise than I see with my 20 crystals unit. Perhaps not so surprising, because I am using about 6 decibels more crystals, 20 instead of 6, so that is almost a factor of 4. The reported performance is at 10 Hz here, minus 150, and that is 6 decibels worse than the minus 156 that I can see. And of course at 1 Hz, the combination of the 6 oscillators does not work well, so one can see only minus 120, which is the performance of a single oscillator. So what we can see essentially is a 6 dB improvement using 6 crystals, and that is valid all the way down to 10 Hz from the carrier. My brute force solution, using 20 crystals to get 20 times more power in the crystals, which is favorable for the signal-to-noise ratio. It is no longer the best way to get a very low noise from a 10 MHz oscillator. This is a fairly recent paper showing an optical method. This is from year 2013, so it's not the latest. But what they present is astonishing. What they report at 10 MHz is minus 145 dBc per Hertz. Unprecedented phase noise levels, it is written here. But the way they do this is very complicated. It is dividing down an optical source. And maybe this can be done in less complicated ways in the future, or maybe already now. I'm not sure, I have seen the latest papers. But using crystals is fairly simple, even if you use many of them. So for many purposes the optical route is probably far too complicated, and using many crystals could be a way of getting a little better than what is the standard today. What they report at 10 MHz is minus 145 dBc per hertz. Unprecedented phase noise levels, it is written here. But the way they do this is very complicated. It is dividing down an optical source. And maybe this can be done in less complicated ways in the future, or maybe already now. I'm not sure, I have seen the latest papers. But using crystals is fairly simple, even if you use many of them. So for many purposes, the optical route is probably far too complicated, and using many crystals could be a way of getting a little better than what is the standard today.
What you see here is what you can find on many places on the internet. The impedance as a function of frequency and the equivalent circuit diagram. So what we see is that outside the actual resonance of the quartz, the mechanical movement, we have a capacitance. And far out on both sides, it is this capacitor, the parallel capacitance. I am calibrating this network analyzer with open and short on this crystal holder. And this is open. This is short. There is a small wire soldered between the pins of this defective crystal. And when prompted to put the 50 ohm dummy load, I put it directly on the network analyzer because there is a 50 ohm system from this point up to the crystal holder. With nothing connected, I now see a very high impedance, nearly 40 kilo ohms. With a crystal in the holder, I see this. This almost horizontal line is the parallel capacitor. The impedance of a capacitor decreases as the frequency increases, but the frequency span is only 1 MHz at the center frequency of 10 MHz. I can compensate for the capacitance by setting the electrical delay. Now I have compensated for the parallel capacitance, so now I can have a closer look to what originates in the crystal. Here is the main resonance, and that was just statistics, but here are other resonances, spurious resonances, but I'm not interested in them at this time. Now the sweep is 10 kilohertz. And as you can see, the impedance goes towards the series resonance as straight lines, all the way 10 kilohertz on both sides, almost straight lines. And of course, there is noise when we come far from the series resonance. But I'm interested in the closer range. Now the sweep width is 100 Hertz only. And you can see the impedance goes from capacitive 800 ohms down to resistive 64 ohms, and then inductive up to 800 ohms. And we can see that the inductance is growing linearly in the range from the series resonance and 10, 20, 30 perhaps kilohertz upwards. But we don't want a very high inductance, so normally one would use the crystal somewhere in this region. And in an oscillator, the crystal is just an inductance at the particular frequency of oscillation. Here I have connected 3 crystals in parallel. And then I see a peculiar pattern, but if I look at the impedance magnitude, it is not very peculiar. We have 3 different resonances. They are separated by 5 Hertz at 75 degrees, and it's different at room temperature, and I don't want to worry about it. The sweep width here is 200 Hertz, so the total width here is 30 Hertz. But one has to go to a frequency above the frequency where any of them is capacitive. To make a parallel LC resonator with these crystals in parallel, I would need a capacitor of about 75 pF. Here is a crystal filter with those 3 crystals in parallel. What I then see with a span of 200 Hertz is the region where there is one of them is capacitive, so I get something on the response curve, but that is insignificant because oscillations will occur at the main peak, and if I look at the bandwidth, I find Q is 1.23 million. So I've certainly not lost Q by putting them in parallel. Now there is only one crystal. I have removed the other 2. And then this is what I see. Q was 1.23, but now bandwidth still 1.23. But the frequency is significantly lower because the inductance is 3 times higher. But I can go back to the original frequency by reducing the parallel capacitor. Now the capacitor is much smaller, should be 3 times smaller roughly, and now it says Q is 1.17 million, so it is a little bit less. This is the crystal filter I used. This network down here is to provide a signal in antiphase from input to output, because there is the capacitive coupling straight through, and this does not attenuate that coupling. It just has on the resonance, it doesn't attenuate it, and that gives the full signal. And off resonance, the impedance here does not go down to 0, it goes to some low value. When doing this trick of connecting crystals in parallel, one should select them for the same resonance frequency, because we want the current through the crystals to be the same. So this showing that with 5 Hertz differences in frequency, no disaster happens. But for actual experiments, I want them to be within 1 Hertz or so. Here is the general block diagram of an oscillator. There is an amplifier, something to control the amplitude, something to control the phase, something to control the impedance level, and then a filter and then again impedance control, back to the amplifier. And we need the phase shift from here to be 0 degrees. And we set that with a phase control. And amplitude control could be simply that the amplifier saturates, or that we have something that saturates separately, or a amplitude control feature of some kind, a FET perhaps. And then there is an amplifier, a buffer, to isolate the output from the loop, so that varying impedances here do not change the properties of the oscillation too much. There are two ways of arranging the filter. When we talk about crystals, means LC filters, we can feed with a very high impedance to the parallel resonance like this, or we can feed with a current into the loop, and then we need a very low impedance. In both cases, to not degrade the Q. And to take out the energy, it's the same, a high impedance load up here, or a low impedance load in series with a current. Oscillators are often very simple. Here we have a capacitive voltage divider. The low impedance output of the source, it's up-transformed by the resonator and the capacitive voltage divider to feed a slightly larger voltage of the same phase onto the base of the transistor. And this is an improvement. We can have another voltage divider, so we have a very low impedance, not so high impedance, and a very high impedance up here. And we can have a tap on the coil to take the collector voltage and then take it in antiphase to the base, because the transistor is going to make a 180 degree phase shift, which we have to compensate for. And there are other architectures. Limiting is just that the transistor saturates in these cases. So we can have high impedance input and high impedance output. And I symbolize that with a field effect transistor. And I don't worry about the DC currents for the active elements. Or we can have a high impedance input and a low impedance output. Then we want the input impedance of this amplifier very low. Or we could put it at the capacitor also. It doesn't matter, because it is a circulating current in the LC circuit. We want to measure the current. And then we can have a low impedance in and a low impedance out. And normally one would draw the schematic like this. Means the crystal is connected from the input to the output of a non-inverting amplifier. And we can have low impedance input and high impedance output. I think this one is very attractive because we can have an amplifier with feedback to generate a very low impedance, which will degrade the Q very little. And we can have a very high impedance, maybe with a FET, or maybe something else, but as an emitter or source follower, which gives a very high impedance at this point. And what is best, I don't know. This depends on how much we load the LC resonator, that means degrade the Q, but also on the noise properties of the amplifier in use. I have made an experiment with the high to high configuration. This one, using 20 crystals for this resonator, plus a large fixed capacitor. And the result is very encouraging. with a noise level that is far better than anything published about crystal oscillators in the literature. You can see about that in the nerds110 video, the one immediately before this one, and also in the one before that, nerds108. When we connect several crystals in parallel, and in parallel with a rather big capacitor, n times bigger than we would have with just a single crystal, to create a resonance. On the resonance frequency, the impedance is resistive. And what we know is that the impedance on the resonance is going to be reduced when we parallel these resistances from each crystal. So the resistive impedance on the resonance frequency is going to be the impedance of one crystal divided by n. It means that the noise voltage, which is this formula, square root of 4 times Boltzmann's constant, gånger the absolute temperature, times the resistance and the bandwidth. I can write that as a square root of a constant divided by the number of crystals. And the signal voltage we can apply is determined by the signal voltage that each crystal can take, because the crystal is specified to have a maximum power, and that is given by the current through the losses in the crystal, which is typically 60 or 80 ohm or something like that. And depending on the frequency, that is the size of the capacitor essentially, or the frequency offset from the series resonance frequency of the crystal itself, that signal voltage that we can apply is constant. And that means that the signal-to-noise ratio, signal voltage over noise voltage squared, because signal-to-noise ratio, we want to express that as a power ratio, and the power ratio is the voltage ratio squared. So the signal-to-noise ratio is another constant times the number of parallel crystals. And there is another way of finding the same conclusion. The noise power of any resistor is signal voltage squared divided by the resistance. And that is 4 times Boltzmann's constant gånger absolute temperature gånger bandwidth. This is really the fundamental property of a resistor. And the maximum signal power is the maximum power for each crystal multiplied by the number of crystals. And that gives us the same as we had before. The noise power is a constant, and the signal power is proportional to the number of crystals. And it gives us this formula in a much simpler way.